Close your eyes and take a deep breath. Let the weight of the day melt away as we embark on a journey unlike any other, a journey through the vast, shimmering tapestry of the universe. Picture yourself floating effortlessly among the stars, where galaxies stretch endlessly in every direction, and the mysteries of the cosmos unfold before you. This is not just a story, it is an invitation to explore the grand design of existence itself, to wander through the intricate web of light and darkness that binds everything together. As you settle in, let your mind drift, free from the confines of Earth, and allow the soothing rhythm of the cosmos to guide you into a state of deep relaxation. Together, we will uncover the secrets of the universe's large-scale structure, a breathtaking dance of galaxies, dark matter, and cosmic forces that has shaped everything we know. So, wherever you are, whatever time it is, let go of the world around you and join us on this tranquil voyage through the stars. The universe is waiting. Now, let us turn our gaze to the cosmic web, the invisible framework that holds the universe together. Imagine a vast, shimmering network stretching across the cosmos, like threads of light woven into an intricate tapestry. This is the cosmic web, a structure so immense it defies comprehension. It is made up of galaxies, dark matter, and clouds of gas, all connected in a delicate balance. Picture it as a spider's web, but on a scale so grand that entire galaxies are mere specks, caught in its threads. These filaments of light and matter stretch across billions of light years, forming the backbone of the universe. They are the highways along which galaxies travel, the bridges that link clusters of stars and planets. And yet, much of this web remains hidden, cloaked in darkness, waiting to be discovered. As you drift through this cosmic network, let your mind wander along its pathways, tracing the invisible lines that bind the universe together. This is the cosmic web, a masterpiece of nature, a testament to the beauty and complexity of the cosmos. Now, let us journey deeper into the cosmic web, where galaxies shine like bustling cities in the vast expanse of the universe. Picture these galaxies as vibrant metropolises, each one teeming with billions of stars, planets, and countless mysteries waiting to be explored. Just as cities are connected by roads and highways, galaxies are linked by the filaments of the cosmic web, forming clusters and superclusters that stretch across unimaginable distances. These clusters are like neighborhoods in the universe, where galaxies gather in groups, bound together by gravity. Some clusters are small and intimate, while others are sprawling and dense, home to thousands of galaxies. Within these cosmic cities, stars are born, planets form, and black holes lurk in the shadows, shaping the destiny of their galactic homes. As you drift through this cosmic landscape, notice how galaxies are not scattered randomly, but instead gather in patterns, clustering together in ways that reveal the hidden architecture of the universe. These gatherings are not just random collections, but are shaped by the gravitational pull of dark matter, the invisible force that guides their movements. Each galaxy, with its swirling arms and glowing core, is a world unto itself, yet part of a larger community, a cosmic city within the grand design of the universe. As you explore these galactic metropolises, let your imagination wander through their streets of starlight, marveling at the beauty and complexity of these celestial cities. Now, as we venture further into the cosmic tapestry, let us turn our attention to the unseen force that quietly shapes the universe, dark matter. Imagine, if you will, an invisible architect working tirelessly behind the scenes, crafting the grand design of the cosmos. Dark matter, though it cannot be seen, makes its presence known through its immense gravitational pull. It is this mysterious substance that holds galaxies together, preventing them from drifting apart into the void. Without dark matter, the galaxies we see as bustling cities would scatter like leaves in the wind, their stars and planets lost to the emptiness of space. Dark matter weaves the threads of the cosmic web, creating the vast network of filaments and nodes that connect galaxies across the universe. Picture it as the scaffolding upon which the universe is built, an invisible framework that guides the formation of galaxies and clusters. Its gravitational influence is so powerful that it bends the very fabric of space and time, shaping the paths of stars and galaxies as they move through the cosmos. Yet, despite its crucial role, dark matter remains elusive. It does not emit light, nor does it interact with the electromagnetic forces that allow us to see the stars and planets around us. It is a ghostly presence, detectable only through its gravitational effects on the visible universe. Scientists have spent decades searching for clues, using telescopes and sophisticated instruments to map its distribution and understand its nature. What they have discovered is that dark matter makes up a staggering 85% of all matter in the universe, far outweighing the ordinary matter we can see. As you drift through this invisible realm, consider how dark matter shapes not only the galaxies, but also the destiny of the universe itself. It is the silent force that binds the cosmic web, the unseen hand that guides the dance of galaxies across the vast expanse of space. And though it remains hidden from our eyes, its influence is everywhere, a reminder that the universe is far more complex and mysterious than we can imagine. With this understanding of dark matter's role, let us now explore another cosmic mystery: dark energy, the force that drives the universe's expansion and shapes its future. Now, as we shift our gaze to another enigmatic force shaping the cosmos, let us explore the mysterious influence of dark energy. While dark matter acts as the universe's invisible glue, holding galaxies and clusters together, dark energy plays a very different role. It is the force driving the universe's expansion, pushing galaxies apart at an ever-increasing rate. Imagine the universe as a balloon being inflated, with galaxies moving away from each other as the space between them stretches. Dark energy is the breath that fills this cosmic balloon, expanding it faster and faster over time. Unlike dark matter, which pulls matter together through gravity, dark energy works in opposition, counteracting the gravitational forces that bind the universe. This cosmic tug of war between dark energy and dark matter shapes the fate of the universe itself. While dark matter's gravity keeps galaxies clustered in the cosmic web, dark energy's repulsive force pushes them apart, creating vast voids and stretching the fabric of space. Scientists first discovered dark energy in the late 1990s, when observations of distant supernovae revealed that the universe's expansion was accelerating, not slowing down as previously thought. This discovery was a profound surprise, challenging our understanding of the cosmos. Today, we know that dark energy makes up about 68% of the universe's total energy content, dwarfing even the influence of dark matter. Yet, despite its dominance, dark energy remains one of the greatest mysteries in modern science. What exactly is dark energy? The truth is, we don't yet know. Some theories suggest it could be a property of space itself, a constant energy density that permeates the universe. Others propose it might be a dynamic field that changes over time. Whatever its nature, dark energy's effects are undeniable, shaping the large-scale structure of the universe and determining its ultimate destiny. As you ponder this cosmic force, consider how dark energy and dark matter work in tandem to shape the universe. Dark matter builds the cosmic web, while dark energy stretches it, creating the intricate balance that defines our universe. Together, they remind us that the cosmos is a place of both harmony and tension, where unseen forces guide the dance of galaxies across the vast expanse of space. With this understanding of dark energy's role, let us now journey back in time to the very beginning, to the moment when the seeds of the universe's structure were first sown, the Big Bang. Now let us travel back in time to the very moment when the universe as we know it began, the Big Bang. Picture a single point, unimaginably hot and dense, containing all the energy and matter that would one day form galaxies, stars, and planets. In an instant, this point expanded, not into empty space, but creating space itself as it grew. This explosive beginning set the stage for everything that followed, including the intricate cosmic web we see today. In those first moments, the universe was not perfectly smooth. Tiny fluctuations, like ripples on the surface of a pond, existed in the fabric of space and time. These fluctuations were incredibly small, but they held the seeds of the universe's future structure. As the universe expanded and cooled, gravity began to pull matter toward these denser regions, amplifying the differences over billions of years. Think of it like a cosmic game of tug-of-war. The denser regions, where matter was slightly more concentrated, began to attract more and more material, growing into the first clumps of matter. Over time, these clumps merged and grew, forming the first stars, galaxies, and eventually, the vast clusters and filaments of the cosmic web. What's fascinating is that these initial fluctuations were so small that they might seem insignificant. Yet, they were the blueprint for the entire universe. Without them, the cosmos would have remained a featureless sea of particles, with no galaxies, no stars, and no planets. It was these tiny imperfections that allowed the universe to evolve into the rich, complex structure we observe today. Scientists have even been able to map these early fluctuations by studying the cosmic microwave background, the faint afterglow of the Big Bang. This ancient light reveals the patterns of density that existed when the universe was just a few 100,000 years old, offering us a glimpse into its infancy. As you reflect on this, consider how something as small as a fluctuation in the early universe could grow into the vast, interconnected structures we see today. It's a reminder that even the smallest beginnings can lead to extraordinary outcomes, shaping the cosmos in ways we are only beginning to understand. With this foundation laid, let us now turn our attention to the cosmic microwave background itself, the universe's baby picture, and how it helps us unravel the story of the cosmos. Now, let us take a closer look at the cosmic microwave background, often referred to as the universe's baby picture. This faint glow of light, which fills the entire sky, is the oldest light we can observe, dating back to when the universe was just a few 100,000 years old. It's like a time capsule, preserving the conditions of the early cosmos and offering us a direct glimpse into its infancy. Imagine the universe at that time, still hot and dense, filled with a glowing plasma of particles and light. As the universe expanded and cooled, this plasma began to thin out, allowing light to travel freely for the first time. This moment, known as recombination, marked the birth of the cosmic microwave background. The light released during this event has been traveling through space ever since, gradually cooling and stretching into the microwave wavelengths we detect today. What makes this ancient light so remarkable is that it carries the imprint of those tiny fluctuations we discussed earlier. These fluctuations, which began as ripples in the density of matter, left their mark on the cosmic microwave background as subtle variations in temperature. Some regions appear slightly warmer, others slightly cooler, creating a patchwork of light and dark spots across the sky. These temperature variations are incredibly small, just a fraction of a degree, but they hold immense significance. They reveal the seeds of the cosmic web, the blueprint for the large-scale structure of the universe. The warmer spots correspond to regions where matter was slightly denser, while the cooler spots mark areas that were less dense. Over billions of years, gravity amplified these differences, pulling matter together to form galaxies, clusters, and the intricate filaments of the cosmic web. Scientists have mapped the cosmic microwave background with incredible precision, using satellites like the Wilkinson Microwave Anisotropy Probe and the Planck mission. These maps provide a detailed snapshot of the early universe, allowing us to measure its age, composition, and expansion rate with remarkable accuracy. They also confirm the predictions of the Big Bang Theory, offering strong evidence for our understanding of the universe's origins. As you ponder this, consider the cosmic microwave background as a window into the past, a way to see the universe as it was long before stars or galaxies existed. It's a reminder that the cosmos is not static, but constantly evolving, shaped by the forces of gravity and the echoes of its earliest moments. With this understanding, let us now turn our gaze to the largest structures in the universe, superclusters, vast collections of galaxy clusters that stretch across hundreds of millions of light years. These cosmic giants are the next chapter in our journey through the large-scale structure of the universe. Now, as we venture further into the vastness of the cosmos, we encounter superclusters, the titans of the universe's large-scale structure. These immense assemblies of galaxy clusters are not just large, but they are the largest known structures in existence, stretching across hundreds of millions of light years. To put this into perspective, if a single galaxy were the size of a city, a supercluster would span an entire continent, connecting countless cities in a sprawling cosmic network. Superclusters are not random collections of galaxies, but are organized into intricate patterns, shaped by the gravitational pull of dark matter and the expansion of space itself. They form the dense nodes of the cosmic web, where filaments of galaxies and gas converge, creating regions of incredible density and activity. Within these superclusters, galaxy clusters collide and merge, triggering bursts of star formation and feeding supermassive black holes at their centers. One of the most famous superclusters is the Laniakea supercluster, which includes our own Milky Way galaxy. Laniakea, meaning immense heaven in Hawaiian, spans over 500 million light years and contains around 100,000 galaxies. It's a humbling reminder that even our galaxy, vast as it is just one small part of an even greater structure. What makes superclusters so fascinating is not just their size, but their role in the universe's evolution. They act as cosmic crossroads, where the forces of gravity and dark energy play out on a grand scale. While gravity pulls galaxies together, dark energy pushes space apart, creating a delicate balance that shapes the distribution of matter across the universe. As we observe these colossal structures, we begin to see patterns that hint at the universe's underlying order. Superclusters are not isolated islands, but are connected by vast filaments of gas and galaxies, forming a web-like structure that spans the entire observable universe. This interconnectedness reveals the profound unity of the cosmos, where even the largest structures are part of a greater whole. Yet, despite their immense size, superclusters are not static. They are dynamic, ever-changing entities, shaped by the ongoing dance of gravity and expansion. Over billions of years, they will continue to evolve, merging with neighboring superclusters and reshaping the cosmic landscape. As we reflect on these cosmic giants, let us now turn our attention to the spaces between them, the vast, empty regions known as cosmic voids. These voids, though seemingly empty, play a crucial role in the universe's structure, offering a stark contrast to the dense clusters and superclusters that dominate the cosmic web. Now, as we shift our gaze from the bustling superclusters, we find ourselves drawn to the quiet, expansive regions of the cosmos, known as cosmic voids. These vast, seemingly empty spaces stretch across the universe, forming the gaps between the dense filaments of the cosmic web. While they may appear barren at first glance, cosmic voids are far from insignificant. In fact, they play a vital role in shaping the universe's large-scale structure, offering a striking contrast to the crowded galaxy clusters and superclusters we've just explored. Imagine the cosmic web as a sponge, with its intricate network of filaments and nodes. The voids are the hollow spaces within that sponge, making up the majority of the universe's volume. Some of these voids are so immense that they span hundreds of millions of light years, creating regions where galaxies are few and far between. Yet, even in these sparse areas, the universe's story continues to unfold. One of the most fascinating aspects of cosmic voids is their role in the universe's expansion. Because these regions contain less matter, the gravitational pull within them is weaker, allowing space to stretch more freely. This means that voids are expanding faster than the denser regions of the cosmic web, driven by the mysterious force of dark energy. As a result, they act as cosmic accelerators, pushing galaxies apart and influencing the overall structure of the universe. But voids are not entirely empty. Scattered within them are a few isolated galaxies, often referred to as void galaxies. These galaxies are unique, having evolved in an environment vastly different from their counterparts in denser regions. Without the frequent interactions and collisions that occur in galaxy clusters, void galaxies tend to be quieter and more isolated, offering astronomers a rare glimpse into how galaxies evolve in solitude. The study of cosmic voids also provides valuable insights into the distribution of dark matter and dark energy. By mapping the shapes and sizes of voids, scientists can better understand how these invisible forces shape the universe. Voids act as cosmic laboratories, revealing the delicate interplay between gravity and expansion on the largest scales. As we contemplate these vast, empty regions, we are reminded of the universe's incredible diversity. From the dense superclusters to the sparse voids, every part of the cosmic web has a role to play in the grand tapestry of existence. And just as the voids expand, so too does our understanding of the cosmos, revealing new mysteries and deepening our appreciation for its complexity. With this in mind, let us now turn our attention to the intricate threads that connect these voids and superclusters, the filaments and nodes of the cosmic web. These delicate yet powerful structures weave the universe together, forming the backbone of its large-scale architecture. Now, as we move from the vast emptiness of cosmic voids, let us explore the delicate yet powerful structures that bind the universe together, the filaments and nodes of the cosmic web. These intricate threads form the backbone of the universe's large-scale architecture, weaving galaxies and clusters into a grand, interconnected tapestry. Picture the cosmic web as a colossal spider's web stretching across the cosmos. The filaments are the silken strands, thin and elongated, connecting galaxies and clusters like beads on a string. These filaments are made up of dark matter, gas, and galaxies, forming bridges between the denser regions of the universe. They are the highways along which matter flows, guiding the formation and movement of galaxies over billions of years. At the intersections of these filaments lie the nodes, the densest regions of the cosmic web. These nodes are home to galaxy clusters and superclusters, bustling hubs of cosmic activity, where thousands of galaxies gather under the influence of immense gravitational forces. Think of these nodes as the bustling cities of the universe, where galaxies come together to form some of the most massive structures we know. The filaments themselves are not uniform. Some are thick and dense, packed with galaxies and gas, while others are thinner and more diffuse. Yet each filament plays a crucial role in the universe's structure, acting as a conduit for matter and energy. They are the pathways that allow galaxies to grow and evolve, feeding them with the gas and dust needed to form stars and planets. One of the most remarkable aspects of filaments is their ability to reveal the hidden influence of dark matter. While we cannot see dark matter directly, its gravitational pull shapes the filaments, guiding the flow of gas and galaxies along their lengths. By studying these structures, scientists can map the distribution of dark matter and better understand its role in shaping the universe. Nodes, on the other hand, are the anchors of the cosmic web. They are the points where multiple filaments converge, creating regions of intense gravitational activity. These nodes are not only home to galaxy clusters, but also to supermassive black holes, which lurk at the centers of many galaxies, influencing their surroundings in profound ways. Together, filaments and nodes create a dynamic and ever-evolving network, one that has been growing and changing since the early universe. They are the threads that connect the cosmos, from the smallest galaxies to the largest superclusters, forming a structure that is both beautiful and awe-inspiring. As we reflect on these intricate connections, we are reminded of the universe's unity. Every filament, every node, every galaxy is part of a larger whole, bound together by the forces of gravity and the mysteries of dark matter and dark energy. And as we continue to explore this cosmic web, we uncover not only the secrets of the universe's structure, but also our place within it. With this understanding, let us now turn our attention to one of the most intriguing mysteries of the cosmic web, the Great Attractor, a gravitational anomaly that draws galaxies toward it, shaping the motion of the universe on the largest scales. Now, as we venture deeper into the cosmic web, we encounter one of its most enigmatic features, the Great Attractor. Hidden within the vast expanse of the universe, this mysterious gravitational anomaly exerts an irresistible pull on galaxies, drawing them toward it like a cosmic magnet. Its influence stretches across hundreds of millions of light years, shaping the motion of galaxies and clusters on an unimaginable scale. The Great Attractor lies in the direction of the constellation Centaurus, but its exact nature remains shrouded in mystery. What we do know is that it represents a region of immense gravitational power, one that bends the paths of galaxies and alters the flow of the cosmic web itself. Imagine it as a hidden force, quietly orchestrating the movement of countless galaxies, guiding them through the vastness of space. For decades, astronomers struggled to study the Great Attractor directly because it lies behind the dense plane of our own Milky Way galaxy. This region, known as the zone of avoidance, is filled with gas, dust, and stars that obscure our view. Yet, through innovative techniques and advanced telescopes, scientists have begun to peel back the veil, revealing glimpses of this cosmic enigma. What they've discovered is both fascinating and perplexing. The Great Attractor is not a single object, but rather a massive concentration of matter, including galaxy clusters and superclusters, all bound together by gravity. One of the most prominent structures in this region is the Norma cluster, a dense gathering of galaxies that contributes to the overall gravitational pull. But the Great Attractor's influence extends far beyond its immediate surroundings. It is part of an even larger structure known as the Laniakea supercluster, a vast collection of galaxies spanning over 500 million light years. Within this supercluster, the Great Attractor acts as a gravitational focal point, drawing galaxies toward it and shaping the flow of the cosmic web on a grand scale. This motion, known as the bulk flow, reveals how galaxies are not just drifting randomly through space, but are instead moving in a coordinated dance, guided by the gravitational forces of massive structures like the Great Attractor. It's a reminder that the universe is not static, but dynamic, with matter constantly in motion, pulled by the invisible threads of gravity. Yet, the Great Attractor is not the final destination. Beyond it lies an even greater gravitational force, the Shapley supercluster, the largest known concentration of matter in the observable universe. Together, these structures form a cosmic tug of war, shaping the large-scale motion of galaxies and revealing the intricate balance of forces that govern the universe. As we ponder the mysteries of the Great Attractor, we are reminded of how much remains to be discovered. Its hidden nature challenges us to push the boundaries of our knowledge, to peer deeper into the cosmos and uncover the secrets that lie beyond our current understanding. And as we continue to explore, we gain not only insights into the universe's structure, but also a deeper appreciation for the forces that shape our cosmic home. With this in mind, let us now turn our gaze to the bustling metropolises of the universe galaxy clusters, where thousands of galaxies come together under the influence of immense gravitational forces, creating some of the most spectacular sights in the cosmos. Now, as we shift our focus to the bustling hubs of the cosmos, we find ourselves amidst the galaxy clusters, the universe's grand metropolises. These clusters are the densest regions of the cosmic web, where thousands of galaxies gather under the immense pull of gravity, creating some of the most spectacular and dynamic environments in the universe. Picture a galaxy cluster as a thriving city, teeming with activity. Each galaxy within it is like a neighborhood, filled with stars, planets, and cosmic phenomena. But what truly defines these clusters is not just the galaxies themselves, but the vast amounts of dark matter and hot gas that hold them together. This invisible scaffolding creates a gravitational glue, binding the galaxies into a single, cohesive structure. One of the most remarkable features of galaxy clusters is their sheer size. They can span millions of light years, containing hundreds or even thousands of galaxies. The Perseus cluster, for example, is one of the most massive objects in the known universe, with a gravitational influence that shapes the surrounding cosmic landscape. But galaxy clusters are more than just collections of galaxies. They are also cosmic laboratories, offering insights into the fundamental forces that govern the universe. The hot gas within these clusters, known as the intracluster medium, emits X-rays that reveal the cluster's temperature, composition, and even its history. By studying this gas, scientists can trace the formation and evolution of these colossal structures, uncovering clues about the universe's past and future. Galaxy clusters also play a crucial role in the cosmic web's architecture. They often sit at the intersections of filaments, the dense threads of matter that weave through the universe. These clusters act as anchors, pulling in galaxies and gas from their surroundings and growing even more massive over time. In this way, they are not just passive observers, but active participants in shaping the universe's large-scale structure. One of the most fascinating aspects of galaxy clusters is their ability to bend light. Due to their immense gravitational pull, they act as natural lenses, magnifying and distorting the light from objects behind them. This phenomenon, known as gravitational lensing, allows astronomers to study distant galaxies that would otherwise be too faint to observe. It's like having a cosmic magnifying glass, revealing the hidden depths of the universe. As we explore these cosmic metropolises, we are reminded of the interconnectedness of the universe. Galaxy clusters are not isolated islands, but part of a vast, intricate network that spans the cosmos. They are the result of billions of years of cosmic evolution, shaped by the relentless pull of gravity and the mysterious influence of dark matter. And so, as we marvel at the grandeur of galaxy clusters, we are drawn to the next chapter of our cosmic journey: gravitational lensing, a phenomenon that allows us to peer even deeper into the universe's hidden structures. Through this lens, we will uncover the secrets of light itself, bent and shaped by the immense forces of the cosmos. Now, let us turn our gaze to one of the most extraordinary phenomena in the cosmos: gravitational lensing. Imagine light traveling across the vast expanse of space, encountering a massive object like a galaxy cluster. Instead of continuing in a straight line, the light bends, curving around the immense gravitational pull of the cluster. This bending of light, predicted by Einstein's theory of general relativity, is what we call gravitational lensing. Think of it as a cosmic magnifying glass. When light from a distant galaxy passes near a massive object, the object's gravity acts like a lens, distorting and magnifying the light. This can create stunning visual effects, such as multiple images of the same galaxy, or even arcs and rings of light. These distortions are not just beautiful to behold, they are also powerful tools for astronomers. Gravitational lensing allows us to see objects that would otherwise be too faint or too far away to detect. By studying these magnified images, scientists can map the distribution of dark matter within galaxy clusters, revealing the invisible scaffolding that holds the universe together. It's like uncovering a hidden blueprint of the cosmos, one that would remain invisible without the help of these natural lenses. One of the most famous examples of gravitational lensing is the Einstein cross, where a single distant quasar appears as four distinct images around a foreground galaxy. This striking arrangement is a testament to the precision of Einstein's predictions and the intricate dance of light and gravity in the universe. But gravitational lensing isn't just about observing distant objects. It also helps us measure the mass of galaxy clusters with incredible accuracy. By analyzing how much the light bends, astronomers can calculate the total mass of the cluster, including both the visible matter and the elusive dark matter. This has led to groundbreaking discoveries about the universe's composition and structure. Moreover, gravitational lensing provides a unique way to study the expansion of the universe. By observing how the light from distant objects is distorted over time, scientists can track changes in the universe's rate of expansion, offering clues about the mysterious force known as dark energy. As we delve deeper into the phenomenon of gravitational lensing, we begin to see the universe in a new light. Literally, it's a reminder that even the most fundamental aspects of our reality, like light and gravity, are intertwined in ways that continue to astonish and inspire. And so, as we marvel at the bending of light and the secrets it reveals, we are drawn to the next chapter of our cosmic journey, the Hubble Deep Field, a window into the past that allows us to glimpse the universe as it was billions of years ago. Through this extraordinary view, we will uncover the origins of galaxies and the story of our cosmic evolution. Now, let us journey to one of the most profound achievements in the history of astronomy, the Hubble Deep Field. Imagine pointing a telescope at what appears to be an empty patch of sky, a region so small it would be like looking at the universe through a drinking straw. What could possibly be there? The answer, revealed by the Hubble Space Telescope, is nothing short of breathtaking. In the mid-1990s, astronomers directed Hubble's gaze toward a seemingly blank area of the sky, far from the glare of nearby stars. Over the course of 10 consecutive days, the telescope collected light from this tiny region, and the result was astonishing. What appeared to be empty space was, in fact, teeming with thousands of galaxies, each one a sprawling city of stars, planets, and cosmic wonders. The Hubble Deep Field image is like a time machine, capturing light that has traveled across the universe for billions of years. When we look at these galaxies, we are seeing them not as they are today, but as they were when the universe was young. Some of these galaxies formed just a few 100 million years after the Big Bang, offering us a glimpse into the early stages of cosmic evolution. What makes the Hubble Deep Field so remarkable is its ability to reveal the sheer scale of the universe. In a patch of sky, no larger than a grain of sand, held at arm's length, we find thousands of galaxies, each containing billions of stars. This image is a humbling reminder of how vast the cosmos truly is, and how much of it remains unexplored. But the Hubble Deep Field is more than just a stunning photograph. It has transformed our understanding of galaxy formation and the universe's history. By studying these distant galaxies, scientists have uncovered clues about how galaxies grow and evolve over time. They have observed galaxies in various stages of development, from young, chaotic systems to older, more structured ones, painting a picture of cosmic growth and change. The Hubble Deep Field also highlights the power of persistence and curiosity. By focusing on a seemingly empty part of the sky, astronomers were able to uncover a treasure trove of information about the universe. It's a testament to the idea that sometimes the most profound discoveries come from looking where no one else has thought to look. As we marvel at the Hubble Deep Field, we are reminded of our place in the cosmos. These thousands of galaxies, each with its own story, are just a tiny fraction of what lies beyond our own Milky Way. They invite us to ponder the mysteries of the universe and our role within it. And so, as we reflect on the wonders revealed by the Hubble Deep Field, we turn our attention to another monumental effort to map the cosmos, the Sloan Digital Sky Survey. This ambitious project has created detailed three-dimensional maps of the universe, offering new insights into its structure and evolution. Together, these endeavors continue to expand our understanding of the cosmos, one image at a time. Now, let us shift our gaze to another monumental effort in our quest to understand the cosmos, the Sloan Digital Sky Survey. This ambitious project, launched in the year 2000, has revolutionized our ability to map the universe in unprecedented detail. Unlike the Hubble Deep Field, which focused on a tiny patch of sky, the Sloan Digital Sky Survey has cast its net far wider, capturing images and data from over 1/3 of the entire night sky. At its core, the Sloan Digital Sky Survey is a massive collaboration of scientists, engineers, and institutions working together to create a three-dimensional map of the universe. Using a specially designed telescope located in New Mexico, the survey has collected light from millions of galaxies, quasars, and stars. But it's not just about taking pictures. This project also measures the distances to these objects, allowing astronomers to piece together a detailed map of the universe's large-scale structure. One of the most remarkable achievements of the Sloan Digital Sky Survey is its ability to reveal the cosmic web in stunning clarity. By mapping the positions of galaxies and galaxy clusters, the survey has shown how these structures are not randomly scattered, but instead form an intricate network of filaments and voids. These filaments, made up of galaxies and dark matter, stretch across billions of light years, connecting the universe's largest structures. The voids, on the other hand, are vast, empty regions that make up the spaces between these filaments. Together, they create a web-like pattern that defines the universe's architecture. The Sloan Digital Sky Survey has also provided invaluable insights into the history of the universe. By studying the distribution of galaxies at different distances, and therefore different times in the past, scientists have been able to trace how the cosmic web has evolved over billions of years. This has helped us understand how gravity has shaped the universe, pulling matter together to form galaxies and clusters while leaving behind the vast voids we see today. But the survey's contributions don't stop there. It has also played a crucial role in studying dark energy, the mysterious force driving the accelerated expansion of the universe. By measuring the distances to faraway galaxies and observing how their light is stretched by the expansion of space, the Sloan Digital Sky Survey has provided some of the strongest evidence for dark energy's existence. What makes the Sloan Digital Sky Survey truly remarkable is its accessibility. The data collected by the survey is freely available to scientists and the public alike, enabling countless discoveries and inspiring new generations of astronomers. From mapping the Milky Way's structure to identifying distant quasars, the survey has become a cornerstone of modern astronomy. As we reflect on the achievements of the Sloan Digital Sky Survey, we are reminded of the power of collaboration and innovation in unraveling the mysteries of the cosmos. This project has not only deepened our understanding of the universe's structure, but also highlighted the interconnectedness of all things, from the smallest galaxies to the largest cosmic voids. And so, as we continue our journey through the large-scale structure of the universe, we turn our attention to another fascinating phenomenon: cosmic inflation. This rapid expansion of the early universe set the stage for the cosmic web we see today, and understanding it is key to unlocking the secrets of our cosmic origins. Now, let us journey back to the very beginning, to a time when the universe was just a fraction of a second old. This is the era of cosmic inflation, a brief but extraordinary period when the universe underwent an unimaginably rapid expansion. In the blink of an eye, the cosmos grew from a tiny speck to a vast expanse, setting the stage for everything we see today. Cosmic inflation is one of the most profound ideas in modern cosmology. It explains how the universe, in its earliest moments, expanded faster than the speed of light. This might sound impossible, but it's important to remember that this expansion wasn't matter or energy moving through space, it was space itself stretching. Imagine a balloon inflating, with every point on its surface moving away from every other point. That's what happened to the fabric of the universe during inflation, but on a scale and at a speed that defies comprehension. This rapid expansion had a profound impact on the universe's structure. Before inflation, the cosmos was incredibly small and dense, with tiny fluctuations in energy and matter. As the universe expanded, these fluctuations were stretched out, becoming the seeds of the cosmic web we see today. Without inflation, the universe would have remained too smooth and uniform for galaxies and clusters to form. It was this stretching that created the slight variations in density, which gravity later amplified into the vast network of galaxies, filaments, and voids. But how do we know inflation actually happened? One of the key pieces of evidence comes from the cosmic microwave background radiation, the afterglow of the Big Bang. This faint glow, which fills the entire universe, carries tiny temperature variations that match the predictions of inflation. These variations are like fingerprints, revealing the initial conditions of the universe and confirming that it underwent a period of rapid expansion. Inflation also helps explain why the universe appears so uniform on large scales. No matter where we look, the distribution of galaxies and the cosmic microwave background are remarkably similar. This uniformity is a direct result of inflation, which stretched the universe so quickly that even regions far apart today were once close enough to interact and reach equilibrium. As we reflect on cosmic inflation, we begin to see how this brief but transformative event shaped the universe's destiny. It laid the groundwork for the cosmic web, the intricate network of galaxies and voids that defines the large-scale structure of the cosmos. And it set the stage for the emergence of stars, planets, and ultimately, life itself. With this understanding of inflation, we can now turn our attention to another fascinating phenomenon, baryon acoustic oscillations. These ripples in the distribution of matter are like echoes from the early universe, offering clues about how the cosmic web formed and evolved over billions of years. Now, let's explore a fascinating phenomenon that acts as a cosmic echo from the early universe, baryon acoustic oscillations. These ripples in the distribution of matter are like the universe's way of leaving behind a fingerprint, offering us a glimpse into its earliest moments and how it evolved over billions of years. Baryon acoustic oscillations, often referred to as BAOs, are subtle patterns in the way galaxies are spread across the cosmos. Think of them as gentle waves frozen in time, imprinted on the universe when it was just a few 100,000 years old. Back then, the universe was a hot, dense soup of particles, with matter and light tightly coupled together. As the universe expanded and cooled, this soup began to thin out, allowing light to travel freely for the first time. This moment, known as recombination, marked the birth of the cosmic microwave background radiation and set the stage for the formation of BAOs. During this early period, pressure waves rippled through the cosmic soup, much like sound waves traveling through air. These waves pushed matter outward, creating regions of higher and lower density. When the universe cooled enough for atoms to form, these waves froze in place, leaving behind a distinct pattern in the distribution of matter. Over time, gravity took over, pulling matter together to form galaxies and clusters, but the imprint of those early waves remained. Today, we can see these imprints as a subtle clustering of galaxies, spaced at regular intervals across the universe. By measuring the distance between these clusters, astronomers can use BAOs as a kind of cosmic ruler. This allows us to map the universe's expansion over time and understand how dark energy has influenced its growth. What makes BAOs so remarkable is their consistency. No matter where we look in the universe, these ripples appear at the same scale, providing a reliable benchmark for measuring cosmic distances. This uniformity makes BAOs an invaluable tool for studying the large-scale structure of the universe and testing our theories about its evolution. As we delve deeper into the mysteries of baryon acoustic oscillations, we uncover not just the story of how galaxies formed, but also the broader narrative of the universe's expansion. These ripples are a testament to the interconnectedness of cosmic history, linking the earliest moments of the universe to the vast web of galaxies we see today. With this understanding of BAOs, we can now turn our attention to another key force that has shaped the universe: gravity. From the smallest particles to the largest structures, gravity has played a pivotal role in weaving the cosmic web and determining the fate of the cosmos. Now, let's shift our focus to one of the most fundamental forces in the cosmos: gravity. This invisible yet powerful force has been the architect of the universe, shaping everything from the tiniest particles to the grandest structures we see today. Gravity is the force that pulls matter together, and it has been at work since the very beginning of the universe. In the early moments after the Big Bang, tiny fluctuations in the density of matter were amplified by gravity, causing regions of higher density to attract more matter. Over billions of years, this process led to the formation of stars, galaxies, and the vast cosmic web that connects them all. On the smallest scales, gravity binds atoms together to form molecules, and molecules to form planets. It's the reason we stay grounded on Earth, and the reason planets orbit stars. But gravity's influence doesn't stop there. On larger scales, it pulls galaxies into clusters and clusters into superclusters, creating the intricate network of filaments and voids that make up the cosmic web. One of gravity's most fascinating roles is in the formation of galaxy clusters, the universe's largest gravitationally bound structures. These clusters are like cosmic metropolises, home to hundreds or even thousands of galaxies, all held together by the relentless pull of gravity. Within these clusters, galaxies move at incredible speeds, their paths shaped by the gravitational influence of both visible matter and the mysterious dark matter that permeates the universe. But gravity isn't just a force of attraction, it's also a force of balance. In the early universe, gravity worked in tandem with the outward pressure of radiation to create the conditions necessary for structure formation. As the universe expanded and cooled, gravity took the lead, pulling matter into the dense regions that would eventually become galaxies and clusters. Even today, gravity continues to shape the universe. It governs the motion of galaxies within clusters, the orbits of stars within galaxies, and the paths of planets around stars. It's the force that keeps the cosmic web intact, ensuring that the universe remains a dynamic and interconnected tapestry. As we look to the future, gravity will play a crucial role in determining the fate of the cosmos. Will the universe continue to expand forever, pulled apart by dark energy? Or will gravity eventually win out, causing the universe to collapse back in on itself? These are questions that scientists are still working to answer. But one thing is certain: gravity will remain a central player in the story of the universe. With this understanding of gravity's profound influence, we can now turn our attention to another cosmic mystery: the fate of the cosmic web itself. How will the structures we see today evolve over billions of years? And what role will gravity play in their ultimate destiny? As we ponder the immense structures of the universe, let's take a moment to consider what lies ahead for the cosmic web. This vast network of galaxies, clusters, and filaments has been shaped by gravity over billions of years, but its future is far from certain. The fate of the cosmic web is deeply intertwined with the mysterious forces that govern the universe, particularly dark energy. Dark energy, the enigmatic force driving the accelerated expansion of the universe, plays a pivotal role in shaping the cosmic web's destiny. Unlike gravity, which pulls matter together, dark energy pushes space itself apart. This tug of war between gravity and dark energy will determine how the cosmic web evolves over time. One possibility is that dark energy will continue to dominate, causing the universe to expand faster and faster. In this scenario, the cosmic web would gradually stretch and thin out. Galaxies and clusters, once bound together by gravity, would drift farther apart. Over trillions of years, the filaments of the cosmic web could become so stretched that they eventually dissolve, leaving galaxies isolated in an ever-expanding void. On the other hand, some theories suggest that dark energy might weaken over time, allowing gravity to regain its influence. If this happens, the expansion of the universe could slow down, and gravity might once again pull matter together. In this case, the cosmic web could continue to grow denser, with galaxies and clusters merging into even larger structures. There's also the intriguing possibility that dark energy could change in unexpected ways. Some scientists speculate that it might grow stronger, leading to a scenario known as the Big Rip. In this dramatic outcome, dark energy would become so powerful that it tears apart not only the cosmic web, but also galaxies, stars, and even atoms themselves. While this is an extreme possibility, it highlights the profound uncertainty surrounding the universe's ultimate fate. As we look to the distant future, it's clear that the cosmic web is not a static structure. It's a dynamic, ever-changing tapestry, shaped by the interplay of gravity, dark energy, and the fundamental forces of nature. Whether it stretches into oblivion, collapses back on itself, or meets some other fate, the cosmic web will continue to tell the story of the universe's evolution. With these possibilities in mind, we can now turn our attention to another fascinating concept: the multiverse. Could there be other universes beyond our own, each with its own cosmic web and unique destiny? This idea takes us even further into the mysteries of existence, inviting us to imagine a reality far beyond what we can see. As we explore the mysteries of the cosmic web and its uncertain future, let's venture even further into the realm of the unknown, the multiverse. This idea takes us beyond the boundaries of our own universe, inviting us to imagine a reality where countless other universes might exist, each with its own unique structure and destiny. The concept of the multiverse suggests that our universe is just one of many, perhaps even an infinite number, of universes. These universes could be vastly different from our own, with their own laws of physics, types of matter, and large-scale structures. Some might have cosmic webs similar to ours, while others could be entirely alien, shaped by forces we can't even begin to comprehend. One intriguing possibility is that the multiverse could explain some of the peculiarities we observe in our own universe. For example, the fine-tuning of the laws of physics, why they seem perfectly suited for the existence of galaxies, stars, and life, might be a result of there being countless universes, each with different physical constants. In this view, we simply live in one of the universes where conditions are just right for us to exist. Another fascinating aspect of multiverse theories is the idea of parallel universes. These could be universes that branched off from our own at key moments in cosmic history, following different paths of evolution. In some of these parallel universes, the cosmic web might have formed differently, leading to entirely unique arrangements of galaxies and clusters. While the multiverse remains a speculative idea, it opens up exciting possibilities for understanding the large-scale structure of the universe. If other universes exist, they could offer clues about the nature of dark energy, the role of gravity, and the ultimate fate of cosmic structures. They might even challenge our understanding of what it means for something to be real or possible. As we ponder the multiverse, we're reminded of just how much there is to discover. The universe we know is vast and complex, but it might be just one small part of an even grander cosmic tapestry. Whether or not other universes exist, the idea of the multiverse inspires us to think bigger, to imagine realities beyond our own, and to continue exploring the deepest mysteries of existence. With this in mind, let's now turn our attention to how scientists are using advanced tools and technology to simulate the universe's evolution, giving us a glimpse into how the cosmic web might have formed and how it could change in the future. Now, let's step into the world of cutting-edge technology and innovation, where scientists use the power of supercomputers to unlock the secrets of the universe's evolution. These incredible machines allow us to simulate the cosmos, creating virtual models that help us understand how the large-scale structure of the universe formed and how it might change over time. Supercomputers are like cosmic time machines, capable of processing vast amounts of data and running complex simulations that mimic the behavior of the universe. By feeding these machines with the laws of physics, the properties of dark matter and dark energy, and the conditions of the early universe, scientists can recreate the cosmic web in stunning detail. These simulations show us how tiny fluctuations in the early universe grew into the intricate network of galaxies, clusters, and filaments we observe today. One of the most remarkable aspects of these simulations is their ability to predict the future of the cosmic web. By adjusting the parameters, such as the amount of dark energy or the strength of gravity, scientists can explore different scenarios for how the universe might evolve. Will the cosmic web continue to expand and thin out as dark energy dominates, or will gravity eventually pull everything back together, leading to a cosmic collapse? These simulations give us a glimpse into the possible fates of our universe, But simulating the universe isn't just about predicting the future. It's also a powerful tool for testing our theories about the cosmos. For example, by comparing the results of simulations with real observations from telescopes, scientists can check whether their models accurately reflect the universe we live in. If the simulations match the observations, it gives us confidence that our understanding of the universe is on the right track. If they don't, it's a sign that we might need to rethink some of our assumptions. These simulations also help us explore the role of dark matter in shaping the cosmic web. By modeling how dark matter clumps together under the influence of gravity, scientists can see how it forms the invisible scaffolding that galaxies and clusters are built upon. This has led to fascinating discoveries, such as the realization that dark matter halos, the dense regions of dark matter that surround galaxies, play a crucial role in determining how galaxies form and evolve. As we continue to refine these simulations, they become more detailed and accurate, offering us an ever clearer picture of the universe's structure. They allow us to ask questions that would be impossible to answer otherwise, like what the universe looked like in its earliest moments, or how it might appear billions of years from now. With each new simulation, we gain a deeper understanding of the cosmic web and the forces that shape it. And as we look ahead, these virtual universes will continue to guide our exploration, helping us uncover the mysteries of the cosmos, one calculation at a time. Now, let's turn our attention to the building blocks of the cosmic web, the galaxies themselves, and explore how they form and evolve within this vast, interconnected structure. Now, let's journey deeper into the cosmic web and uncover the fascinating story of how galaxies, the building blocks of this vast structure, come to life. Galaxies are not just random collections of stars and planets. They are the result of intricate processes that have shaped the universe over billions of years. At the heart of galaxy formation lies the interplay between gravity and the cosmic web. Imagine the universe shortly after the Big Bang, filled with tiny ripples of matter. These ripples, though small, were the seeds of everything we see today. Over time, gravity began to pull these ripples together, causing matter to clump into denser regions. These clumps grew larger and larger, eventually forming the first galaxies. But how exactly does this happen? Picture a vast ocean of gas, mostly hydrogen and helium, spread across the early universe. Gravity acts like a cosmic sculptor, pulling this gas into denser pockets. As these pockets grow, they heat up, and the gas begins to collapse under its own weight. This collapse triggers the birth of stars, and as more stars form, they gather into what we recognize as galaxies. Dark matter plays a crucial role in this process. While we can't see it directly, its gravitational pull helps hold galaxies together. Think of dark matter as the invisible framework that supports the visible universe. Without it, galaxies would fly apart, unable to maintain their shape. Galaxies don't form in isolation, though. They are deeply connected to the cosmic web, growing along the filaments of dark matter that stretch across the universe. These filaments act like highways, guiding gas and matter into the densest regions, where galaxies form and grow. Over time, galaxies cluster together, pulled by gravity into groups and superclusters. creating the intricate patterns we see in the cosmic web today. But galaxy formation isn't a one-time event. It's an ongoing process. Even today, galaxies continue to evolve, merging with one another and growing as they pull in more gas and dust. These mergers can trigger bursts of star formation, lighting up the universe with new stars and reshaping the galaxies involved. As we look out into the cosmos, we see galaxies in all stages of life, from young, star-forming galaxies to ancient, elliptical galaxies that have long since stopped forming new stars. Each one tells a story, a chapter in the grand narrative of the universe's evolution. Understanding how galaxies form and grow helps us piece together the history of the cosmic web. It shows us how the universe has transformed from a smooth, featureless expanse into the rich, complex structure we see today. And as we continue to study these processes, we gain new insights into the forces that shape not just galaxies, but the entire universe. With this understanding of galaxy formation, let's now turn our gaze to the hidden fuel that powers these cosmic cities, the intergalactic gas that flows through the cosmic web, feeding galaxies and shaping their destiny. Now, let's shift our focus to the invisible yet vital force that flows through the cosmic web, intergalactic gas. This vast reservoir of gas, mostly hydrogen and helium, is the lifeblood of galaxies, fueling their growth and shaping their evolution. While it may seem empty, the space between galaxies is far from barren. It's filled with this diffuse gas, which plays a critical role in the story of the universe's structure. Imagine the cosmic web as a network of rivers and streams, with intergalactic gas flowing along its filaments. This gas doesn't just sit idly, it moves, pulled by gravity, toward the densest regions of the universe. As it travels, it feeds galaxies, providing the raw material needed to form new stars and planets. Without this constant supply of gas, galaxies would eventually run out of fuel, and star formation would come to a halt. But how does this gas make its way into galaxies? Picture a galaxy as a cosmic sponge, soaking up gas from its surroundings. As gas flows along the filaments of the cosmic web, it's drawn into the gravitational pull of galaxies. Once inside, it cools and condenses, forming dense clouds that collapse under their own weight. These collapsing clouds ignite the birth of new stars, lighting up the galaxy and driving its evolution. Intergalactic gas isn't just a passive player, though. It also influences the shape and structure of galaxies. When gas flows into a galaxy, it can trigger bursts of star formation, creating bright, active regions. Over time, this process shapes the galaxy's appearance, from spiral arms to elliptical forms. The gas also interacts with other forces, such as magnetic fields and cosmic winds, adding layers of complexity to its role in galaxy evolution. Interestingly, intergalactic gas isn't evenly distributed. Some regions are rich with gas, while others are nearly empty. These variations create a dynamic environment where galaxies in gas-rich regions grow faster and more vigorously than those in sparse areas. This uneven distribution is another way the cosmic web shapes the universe, influencing where and how galaxies form and evolve. As we study intergalactic gas, we gain a deeper understanding of the universe's life cycle. It's a reminder that even the seemingly empty spaces between galaxies are teeming with activity, playing a crucial role in the grand story of the cosmos. With this understanding of intergalactic gas, let's now turn our attention to the bright beacons that light up the cosmic web, quasars, the luminous centers of distant galaxies that help us map the universe's hidden structures. Now, let's journey deeper into the cosmic web, where some of the most brilliant objects in the universe shine like lighthouses in the vast darkness. Quasars. These extraordinary phenomena are the luminous hearts of distant galaxies, powered by supermassive black holes at their centers. As we explore quasars, we'll uncover how these dazzling beacons illuminate the hidden structures of the universe and help us map its grand design. Quasars are among the most energetic objects in existence, emitting light that can outshine entire galaxies. This incredible brightness comes from the supermassive black holes at their cores. As matter spirals into these black holes, it heats up to extreme temperatures, releasing vast amounts of energy in the form of light and radiation. This process makes quasars visible across staggering distances, allowing us to observe them even from the farthest reaches of the cosmos. But quasars are more than just cosmic light shows. They are also invaluable tools for astronomers. Because they're so bright, quasars act like cosmic flashlights, illuminating the gas and dust that lie between them and us. As their light travels through the universe, it passes through the filaments and voids of the cosmic web. Along the way, this light interacts with the intergalactic gas, leaving behind subtle fingerprints that reveal the structure and composition of the universe. One of the most fascinating ways quasars help us study the universe is through a phenomenon called absorption lines. When quasar light passes through clouds of gas, certain wavelengths of light are absorbed, creating dark lines in the spectrum of the quasar's light. By analyzing these lines, scientists can determine the composition, temperature, and density of the gas, as well as its location within the cosmic web. This information helps us piece together the intricate network of filaments and nodes that make up the universe's large-scale structure. Quasars also provide a glimpse into the early universe. Because they are so distant, the light we see from them has traveled for billions of years, offering a window into a time when the universe was much younger. By studying quasars, we can learn about the conditions of the early cosmos, including how galaxies formed and evolved over time. Interestingly, quasars aren't just passive markers of the universe's structure, they also play an active role in shaping it. The intense radiation and powerful jets emitted by quasars can heat and push surrounding gas, influencing the formation of stars and galaxies in their vicinity. This interplay between quasars and their environments adds another layer of complexity to the cosmic web, highlighting the dynamic nature of the universe. As we continue to study quasars, we uncover more about the universe's hidden architecture. These brilliant beacons not only light up the cosmic dark, but also guide us in understanding the vast, interconnected network that defines the cosmos. With quasars illuminating the way, let's now turn our attention to another essential tool in our cosmic toolkit, the cosmic distance ladder, which helps us measure the vast expanses of the universe with remarkable precision. Now, as we step away from the brilliant glow of quasars, let's explore the tools that allow us to map the vastness of the cosmos, the cosmic distance ladder. This ingenious system of measurement helps astronomers determine how far away objects are, from the stars in our own galaxy to the most distant galaxies billions of light years away. At the base of the cosmic distance ladder are nearby stars, whose distances can be measured using a method called parallax. Imagine holding your finger in front of your face and closing one eye, then the other. Your finger appears to shift against the background. Astronomers use a similar principle, observing how a star's position seems to shift when viewed from opposite sides of Earth's orbit around the Sun. This tiny shift, called parallax, allows us to calculate the star's distance with remarkable precision. For stars farther away, parallax becomes less effective, so astronomers turn to another tool: standard candles. These are objects with known brightness, such as certain types of stars called Cepheid variables. Cepheid stars pulsate in a predictable way, and their brightness is directly related to the length of their pulsation cycle. By measuring how bright a Cepheid star appears from Earth and comparing it to its known brightness, astronomers can determine its distance. When we venture beyond our galaxy, the cosmic distance ladder extends even further. Here, astronomers use supernova exploding stars as standard candles. Type 1, a supernova in particular, are incredibly useful because they all explode with roughly the same brightness. By observing how bright a supernova appears, scientists can calculate its distance, even if it's in a galaxy millions or billions of light years away. But the cosmic distance ladder doesn't stop there. For the most distant objects, like quasars and galaxies at the edge of the observable universe, astronomers rely on redshift. As light travels through the expanding universe, its wavelengths stretch, shifting toward the red end of the spectrum. The greater the redshift, the farther away the object is. By measuring this redshift, scientists can estimate the distance to some of the most remote corners of the cosmos. Each rung of the cosmic distance ladder builds on the one before it, creating a seamless chain of measurements that stretches from our own backyard to the farthest reaches of space. Without this tool, we wouldn't be able to map the universe's structure or understand its scale. As we continue our journey, let's turn our attention to another cosmic mystery: the role of black holes in shaping the evolution of galaxies, and how these enigmatic objects influence the universe on the grandest scales. Now, as we delve deeper into the mysteries of the cosmos, let's turn our gaze toward one of the most fascinating and powerful forces in the universe: supermassive black holes. These enigmatic giants, often found at the centers of galaxies, play a crucial role in shaping the evolution of the galaxies they inhabit. At the heart of nearly every large galaxy lies a supermassive black hole, millions or even billions of times more massive than our Sun. These colossal objects are not just passive residents, they actively influence their surroundings. As matter spirals into a black hole, it forms a swirling disk of gas and dust, heating up to incredible temperatures and emitting vast amounts of energy. This process, known as accretion, can create some of the brightest objects in the universe: quasars. but the influence of supermassive black holes extends far beyond their immediate vicinity. The energy released during accretion can drive powerful jets of particles and radiation, shooting out into space at nearly the speed of light. These jets can heat up the surrounding gas, preventing it from cooling and collapsing to form new stars. In this way, black holes can regulate star formation, effectively putting a brake on the growth of their host galaxies. At the same time, black holes can also trigger star formation. When the jets and winds from a black hole collide with surrounding gas clouds, they can compress the gas, causing it to collapse and ignite new stars. This dual role, both suppressing and stimulating star formation, makes black holes key players in the life cycle of galaxies. Supermassive black holes also play a critical role in shaping the large-scale structure of the universe. As galaxies collide and merge, their central black holes eventually spiral toward each other, merging into an even larger black hole. These cosmic collisions release gravitational waves, ripples in the fabric of space-time, and can send shockwaves through the surrounding gas, influencing the formation of new galaxies and clusters. The relationship between black holes and their host galaxies is so intertwined that astronomers have discovered a surprising correlation. The more massive a galaxy, the more massive its central black hole. This suggests that black holes and galaxies grow together, each influencing the other's evolution over billions of years. As we continue our journey through the cosmos, let's explore how these supermassive black holes, along with other cosmic forces, contribute to the intricate dance of galaxy formation and evolution, weaving the threads of the cosmic web into the vast tapestry of the universe. Now, let's take a step back, or rather, a look back through the vast expanse of cosmic time. One of the most extraordinary gifts the universe offers us is the ability to peer into its past. When we observe distant galaxies, we're not just seeing them as they are today, we're catching a glimpse of how they appeared billions of years ago. This is because light takes time to travel across the universe, and the farther away an object is, the longer its light has been journeying to reach us. Imagine looking at a galaxy located 10 billion light years away. The light we see today left that galaxy 10 billion years ago, when the universe was still in its youth. By studying these ancient beams of light, astronomers can piece together the story of how galaxies formed, evolved, and interacted over cosmic time. It's like flipping through a photo album of the universe's history, each image capturing a moment frozen in time. This cosmic time travel isn't just about seeing old light. It's about understanding how the universe has changed. For instance, early galaxies were smaller, more chaotic, and filled with young, hot stars. Over billions of years, they grew, merged, and transformed into the majestic spirals and ellipticals we see closer to home. By comparing galaxies at different distances, and thus different ages, we can trace the steps of their evolution, uncovering the processes that shape them. But the journey doesn't stop there. The light from these distant galaxies carries more than just images. It holds clues about the conditions of the early universe. By analyzing the colors and spectra of this ancient light, scientists can measure the composition of early galaxies, the rate of star formation, and even the expansion of the universe itself. It's like decoding a cosmic message, written in the language of light, that tells us how the universe grew from a hot, dense soup of particles into the vast, intricate web we see today. As we continue to explore the universe's past, we're not just uncovering its history, we're also learning about our own origins. The elements that make up our planet, our bodies, and everything around us were forged in the hearts of stars and scattered across the cosmos by supernova and galactic winds. By looking back in time, we're tracing the journey of these elements, from their creation in ancient stars to their role in shaping the galaxies, stars, and planets that fill the universe today. So, as we gaze at the night sky, let's remember that every star, every galaxy, and every beam of light is a window into the past, a reminder that the universe is not just a place, but a story unfolding over billions of years. And with each observation, we're adding another chapter to that story, one that connects us to the cosmos in ways we're only beginning to understand. Next, we'll explore the hidden patterns and symmetries that weave through the universe's large-scale structure, revealing the beauty and order that lie beneath its seemingly chaotic surface. Now, let's turn our attention to the hidden patterns and symmetries that quietly shape the universe's vast structure. Beneath the seemingly chaotic expanse of galaxies and cosmic voids lies an intricate tapestry of order, where nature repeats itself in mesmerizing ways. One of the most fascinating examples of this is the concept of fractals, patterns that repeat at different scales, creating a kind of cosmic echo. Picture a snowflake with its delicate, branching arms. Now imagine that same branching pattern repeated across the universe, from the way galaxies cluster together to the way gas flows through the cosmic web. Fractals are everywhere, from the smallest leaves on a tree to the largest structures in the cosmos. They remind us that the universe, for all its complexity, is built on simple, repeating rules. But fractals are just one piece of the puzzle. Symmetry also plays a profound role in shaping the universe. Think of a spiral galaxy, its arms winding outward in a perfect, graceful curve. Or consider the hexagonal shapes of Saturn's North Pole, a natural result of atmospheric dynamics. These symmetries aren't just beautiful to look at, they reveal the underlying laws of physics that govern everything from the tiniest particles to the largest galaxies. Even the distribution of galaxies across the universe follows a kind of symmetry. When astronomers map the cosmos, they find that galaxies aren't scattered randomly. Instead, they form clusters, filaments, and walls, creating a web-like structure that stretches across billions of light years. This cosmic web isn't just a random arrangement. It's a reflection of the gravitational forces that have shaped the universe over billions of years. What's truly remarkable is how these patterns and symmetries connect the small to the large. The same forces that shape the spiral arms of a galaxy also influence the way galaxies cluster together. The same mathematical principles that describe the growth of a tree can be used to model the distribution of matter in the universe. It's as if the universe is whispering a secret language, one that we're only beginning to decode. As we explore these hidden patterns, we're reminded that the universe is not just a place of chaos and randomness. Beneath the surface, there's a deep, underlying order, a kind of cosmic harmony that ties everything together. Whether it's the branching of a river delta or the clustering of galaxies. These patterns tell a story of unity and connection, one that spans the entire cosmos. Next, we'll reflect on humanity's place within this vast, intricate web, and how our understanding of the universe's structure helps us see our own existence in a new light. As we step back to consider our place within this grand cosmic tapestry, it's impossible not to feel a sense of awe. Here we are, on a tiny planet, orbiting an ordinary star, nestled within one of billions of galaxies that stretch across the universe. Yet, despite our seemingly insignificant size, humanity has managed to uncover some of the deepest secrets of the cosmos. We've mapped the cosmic web, peered back in time to the universe's infancy, and even begun to understand the forces that shape its vast structure. Think about it, every atom in your body was forged in the heart of a star, billions of years ago. The carbon in your cells, the iron in your blood, even the calcium in your bones, all of it was created in the fiery furnaces of ancient stars and scattered across the universe by supernova explosions. In a very real sense, we are made of stardust, connected to the cosmos in the most intimate way imaginable, and yet our connection to the universe goes even deeper. The same laws of physics that govern the motion of galaxies and the formation of stars also shape our everyday lives. Gravity, which holds galaxies together, also keeps your feet firmly on the ground. The electromagnetic force, which powers the stars, also allows your brain to send signals to your muscles. In this way, the universe isn't just something out there, it's something we carry within us, a part of who we are. But perhaps the most remarkable thing about humanity's place in the cosmic web is our ability to understand it. With nothing but our curiosity and ingenuity, we've built telescopes that can see billions of light years into the past, created supercomputers that simulate the universe's evolution, and developed theories that explain the behavior of everything from the smallest particles to the largest structures. In a universe that seems so vast and indifferent, we've found a way to make sense of it, to find meaning in its patterns and symmetries. This journey of discovery reminds us that, while we may be small, we are not insignificant. Our ability to explore, to question, and to wonder sets us apart. It's what drives us to look up at the night sky and dream of distant worlds, to unravel the mysteries of the cosmos, and to find our place within it. As we drift off to sleep tonight, let's carry this thought with us, that we are part of something far greater than ourselves, a universe filled with beauty, mystery, and endless possibilities. And in that vastness, we've found not only our place, but also our purpose, to explore, to learn, and to marvel at the wonders of the cosmos. Now, as we prepare to conclude our journey, let's take a moment to reflect on the beauty and mystery of the universe's large-scale structure, and how it invites us to dream of what lies beyond. As we bring our cosmic journey to a close, let's take a moment to reflect on the incredible tapestry we've explored. From the intricate filaments of the cosmic web to the vast voids that stretch between galaxies, the universe reveals itself as a place of both order and mystery. We've traced the origins of galaxies back to the seeds of the Big Bang, marveled at the invisible forces of dark matter and dark energy, and glimpsed the echoes of the early universe in the cosmic microwave background. Each discovery reminds us of the universe's boundless complexity and beauty. Tonight, as you rest, let your mind wander through these cosmic wonders. Picture yourself floating among the stars, surrounded by the shimmering light of distant galaxies. Feel the gentle pull of gravity, the same force that shapes the universe, grounding you in this moment. Imagine the vastness of space, not as something distant or unknowable, but as a part of you, a reminder of your connection to everything that exists. The universe is a story still being written, and you are a part of it. As you drift off to sleep, carry with you the sense of awe and wonder that comes from knowing you are part of something so grand. Let the mysteries of the cosmos fill your dreams, and may you wake with a renewed sense of curiosity and wonder. Thank you for joining me on this journey through the large-scale structure of the universe. If you enjoyed this sleep story, don't forget to subscribe to the channel, like this video, and hit the notification bell so you never miss another cosmic adventure. Until next time, sweet dreams, and may the stars guide you through the night.